Everyone knows about the Battle of Britain. The Spitfires, the Hurricanes, the dogfights over the English Channel, the young pilots scrambling to their planes before the engines even stopped turning. It's one of the most studied, most celebrated, most romanticized chapters of the entire Second World War. But there is a piece of that story that almost never gets told properly. A piece that, without exaggeration, without dramatization, without any need to embellish a single detail, is the real reason Britain survived at all. It wasn't the aircraft, it wasn't the pilots, it wasn't Churchill's speeches or the industrial output of the factories or even the courage of the men who flew. All of those things mattered enormously, but none of them would have been enough without something else. Something that most people, even people who consider themselves serious students of the war, walk right past when they tell the story. A chain of radar stations sitting on the coast of Britain, masts rising above cliffs and beaches, antennas spinning in the sea wind. Operators, many of them women, sitting at cathode ray tube screens in dim rooms, watching green blips move across glass, translating those blips into words, and sending those words up a chain of command that ended with a fighter pilot pulling back on his stick and climbing toward the sun. That system was called Chain Home. And if you want to understand why Britain didn't fall in 1940, you need to understand what Chain Home actually was, how it worked, why it almost didn't exist at all, and what happened on the single day that a catastrophic failure in that system nearly handed the Luftwaffe everything they needed to end the fight in one afternoon. If you want to keep hearing stories like this, stories that go deeper than the headlines and find the details that actually changed history, then stick around. This is exactly the kind of thing we do here, and there's a lot more where this came from. Now let's go back to the beginning, because to understand why Chain Home mattered so much, you need to understand what Britain was up against. By the summer of 1940, France had fallen. The British Expeditionary Force had been evacuated from Dunkirk, leaving most of its heavy equipment on the beaches. Germany controlled the coastline from Norway all the way down to the Spanish border. And on the other side of the English Channel, Hermann Göring's Luftwaffe was preparing for something it had never quite attempted before. A sustained air campaign designed not just to destroy an enemy air force, but to break a nation's will to fight and open the door for a ground invasion. The Luftwaffe in the summer of 1940 was the most powerful and most experienced air force in the world. It had been blooded over Spain during the Civil War. It had smashed Poland in 1939 in a campaign so fast and so brutal it introduced a new word to the world's vocabulary. It had torn through France and the Low Countries in a matter of weeks. Its pilots were experienced, its aircraft were good, its commanders were confident, and its numbers were overwhelming. Against this, Britain had Fighter Command. Led by Air Chief Marshal Hugh Dowding, Fighter Command had around 600 frontline aircraft, mostly Hurricanes with a smaller number of Spitfires. The pilots were brave, skilled, and motivated, but they were badly outnumbered, and they were defending an island. Every time a British pilot was shot down over the Channel or over France, that pilot was gone, either dead or captured. Every time a German pilot was shot down over Britain, he might be captured, but he was still gone from the fight. The math was brutal and it favored Germany heavily. Dowding understood this. He had understood it before the Battle of France even began. He had famously desperately written to the Air Ministry during the fall of France, warning that if Britain kept bleeding fighters into a campaign it couldn't win, there would be nothing left to defend the home island. He was largely ignored. He was told to send more squadrons anyway. He refused. That refusal was itself an act of calculated preservation that probably saved Britain. But even with every fighter intact, even with the best pilots in the world, the numbers didn't work. You cannot defend an entire coastline with 600 aircraft, not if you're flying patrols back and forth waiting for an attack to materialize. A fighter aircraft in 1940 had a range of roughly 2 to 3 hours at most in the air before it needed to refuel. Flying constant patrols would exhaust pilots and burn through fuel and engine hours at a rate that would ground the entire force within weeks. And even if you could keep the planes in the air, you had to find the enemy first. At 20,000 feet on a clear day in summer over the English Channel, a formation of German bombers would give a British pilot perhaps 2 to 3 minutes of visual warning before they were overhead. That's not enough time to scramble from the ground, climb to altitude, and position for an interception. You'd need to be already in the air in roughly the right place at roughly the right altitude, moving in roughly the right direction. And with 600 planes trying to cover hundreds of miles of coastline, the odds of that happening by chance were essentially zero. This was the problem that Dowding's entire strategy had to solve, not how to outfight the Luftwaffe. He knew his pilots could do that, aircraft for aircraft. The problem was finding the enemy before the enemy found you, and it was a problem that had no good answer in the summer of 1940. Except it did. Because a scientist named Robert Watson-Watt had spent the previous 5 years building a solution that almost no one outside a very small government committee fully understood. Watson-Watt was not a romantic figure. He was a Scottish physicist, a civil servant in the truest sense, someone who spent his days working in the radio research station at Slough, fiddling with electromagnetic waves and writing reports that most people never read. But in 1934, a question landed on his desk that changed everything. The question came from Henry Tizard, the chairman of a government committee on the Scientific Survey of Air Defense. The committee had been looking at the problem of defending Britain from air attack, and someone had raised the possibility of a so-called death ray, some kind of electromagnetic weapon that could destroy aircraft or kill their pilots at a distance. Tizard passed the question to Watson-Watt. Could radio waves be used as a weapon? Watson-Watt's answer was no. The math didn't work. You couldn't concentrate enough energy in a beam to do meaningful damage to an aircraft at the ranges required. But in thinking through the problem, he had another idea. If you couldn't use radio waves to destroy aircraft, could you use them to detect them? The principle was already understood. If you sent out a pulse of radio energy and that energy bounced back from an object, you could measure the time it took for the echo to return, and from that calculate the distance to the object. This was the basic idea behind what would eventually be called radar, from radio detection and ranging. It wasn't a completely new concept. Scientists in Germany, France, America, and Japan were all exploring similar ideas at roughly the same time. But Watson-Watt did something that the others were slower to do. He stopped thinking about radar as a laboratory curiosity and started thinking about it as a military system. He wrote a paper called Detection and Location of Aircraft by Radio Methods. He calculated that a practical system was achievable with existing technology, and he persuaded Tizard to put money behind testing the idea. On February 26, 1935, on a flat stretch of farmland near Daventry in Northamptonshire, Watson-Watt and his colleague Arnold Wilkins set up a receiver connected to a cathode ray tube and pointed it toward a BBC shortwave transmitter. Then they asked the Air Ministry to fly a Hayford bomber back and forth over the transmitter at a known altitude and distance. What they saw on that cathode ray tube was a blip, a distortion in the received signal caused by the radio waves bouncing off the aircraft and arriving at a slightly different time than the direct signal. It was faint, it was messy, it required interpretation, but it was real. The aircraft was being detected by radio waves at a range of several miles. The people who witnessed that demonstration went back to London and authorized a full program of development immediately. That was how quickly the implications were understood. This wasn't a technical curiosity. This was a revolution in air defense if it could be made to work reliably, at scale, in real operational conditions. The program that followed moved at a speed that is almost difficult to reconcile with the peacetime bureaucracy that surrounded it. Watson-Watt and his team, working at a new research station at Bawdsey Manor on the Suffolk coast, developed a series of transmitter and receiver designs, tested them, discarded what didn't work, kept what did, and began to understand the peculiarities and limitations of the system they were building. Chain Home, as the network eventually became known, was not elegant. It was not the most sophisticated technical solution to the detection problem. The Germans, when they eventually analyzed it, were almost dismissive of how crude it was compared to what their own engineers would have built. And they were right in a narrow technical sense. Chain Home had serious limitations. It couldn't accurately measure the altitude of incoming aircraft. It struggled to distinguish between individual planes within a large formation. It was vulnerable to jamming. It couldn't look down, so low-flying aircraft below a certain height were invisible to it. But none of that mattered as much as one crucial fact. Chain Home worked. And it was built, installed, staffed, and operational along the entire southern and eastern coastline of Britain by the time the Luftwaffe was ready to attack. By September 1939, when Britain declared war on Germany, there were 19 Chain Home stations covering the coast from the Orkneys in the north to the Isle of Wight in the south. Each station consisted of 3 or 4 transmitter towers, typically around 360 feet tall, and a series of shorter receiver towers. The transmitter towers sent out pulses of radio energy on frequencies between 20 and 30 MHz, sweeping a broad arc over the sea toward the European coast. Any aircraft entering that arc would reflect some of those pulses back toward the receiver towers. Operators sitting at cathode ray tube screens inside concrete bunkers at the base of the towers would see the reflected pulses as blips on their screens. From those blips, a trained operator could extract 2 critical pieces of information: the range of the aircraft from the station, calculated from the time delay between the transmitted pulse and the received echo, and the bearing, the direction from which the echo was coming, calculated by comparing the strength of the signal received on aerials pointing in slightly different directions. That information was passed by telephone to a filter room at Fighter Command's headquarters at Bentley Priory in Middlesex. The filter room's job was to take the raw data from multiple radar stations, cross-reference it, eliminate duplications, and produce a coherent picture of what was actually out there. An incoming German formation might be detected by 3 or 4 different chain home stations simultaneously, each giving a slightly different range and bearing. The filter room reconciled those reports and plotted a single track on a large map table, represented by a marker with a number indicating the estimated size of the formation. That plotted track was then passed to the operations room, also at Bentley Priory, where controllers sitting above a large map table watched the tracks being updated every few minutes by WAAFs, Women's Auxiliary Air Force personnel, using long magnetic plotting rods to move markers around the table like chess pieces. Controllers would look at the incoming tracks, assess the threat, and issue orders to the group and sector commanders responsible for specific areas of the country. Those group commanders controlled the actual squadrons. When a track appeared suggesting a major raid heading towards, say, the Thames estuary in London, the 11 group controller at Uxbridge would order specific squadrons to scramble, specifying which direction to fly, which altitude to climb to, and which radio frequency to monitor. The pilots would take off, climb, and receive further course corrections by radio as the radar picture developed. The key to the whole system was time. Radar gave fighter command time, not a lot of time, typically somewhere between 15 and 30 minutes of warning before an incoming formation crossed the English coast. But 15 minutes was enough. A Hurricane or Spitfire could get airborne and climb to interception altitude in that time. Without radar, without that warning, the first indication of a raid would be a German formation appearing over the coast, by which point it was already too late to scramble, climb, and intercept before the bombers reached their targets. But time alone wasn't the most important thing radar gave Dowding. The most important thing was economy of force. Because Dowding knew he couldn't win a battle of attrition against the Luftwaffe. He didn't have enough planes and didn't have enough pilots. Every aircraft he lost that couldn't be replaced, every pilot killed or badly burned, was a permanent subtraction from a force that was already stretched to breaking point. He could not afford to run his fighters at full stretch every day, burning engines, exhausting pilots, wearing out airframes on patrols that might or might not encounter the enemy. Without radar, defending Britain would have required constant standing patrols over all the potential approach routes, simultaneously, all day, every day. The numbers required for that were impossible. Fighter command would have exhausted itself in a month. With radar, Dowding could keep his fighters on the ground, resting, refueling, waiting. The radar network watched the sea. When a raid was detected, Dowding could calculate roughly where it was going, roughly how many aircraft were involved, and send exactly the right number of fighters to exactly the right place at exactly the right time. No wasted sorties. No fuel burned on empty patrols. No pilots worn out from hours of fruitless flying over the channel looking for an enemy that wasn't there. This was the genius of the system, not the technology itself, which was imperfect and partially understood, but the integration of the technology into an operational doctrine that turned a defensive disadvantage, a smaller force defending a fixed position against a larger attacker, into a workable strategy. The Luftwaffe commanders knew something was wrong from the very beginning. Their formation leaders reported that RAF fighters seemed to appear from nowhere, already at altitude, already in position, already climbing out of the sun before the German pilots even knew they'd been spotted. They reported this. Some of them concluded that the British had informers in France, agents watching the airfields and telephoning warnings back to England. Others thought the RAF must be keeping huge numbers of aircraft in the air all the time, burning through resources at an unsustainable rate. A few German intelligence officers guessed the truth. There were reports that the tall towers along the British coast might be some kind of radio detection system. The Luftwaffe actually sent aircraft to investigate, including a famous flight by the German Zeppelin Graf Zeppelin along the British coast, bristling with electronic monitoring equipment, trying to intercept signals from whatever the British were doing with those towers. The monitoring flight found signals but was confused by what it found. Chain home operated on frequencies that were, by later radar standards, extremely low. The Germans expected that a detection system would use short wavelengths, tight beams, rotating antennas. Chain home used long wavelengths, broad beams, and fixed antennas. It didn't look like what the Germans thought radar should look like. Their analysis concluded that whatever those signals were, they probably weren't being used for aircraft detection in any sophisticated sense. This was one of the great intelligence failures of the war, and it had enormous consequences. Because the Luftwaffe never seriously prioritized the destruction of the chain home network. There were some attacks on radar stations during the Battle of Britain, but they were inconsistent, the results were never properly analyzed, and after a relatively short period, the raids on radar stations were largely abandoned as not worth the effort. That decision, which grew at least partly from a failure to understand what the system actually did, was close to suicidal. Because knocking out Chain Home was probably the single thing the Luftwaffe could have done to genuinely cripple British air defense. Everything else, killing pilots, destroying aircraft, bombing airfields, could be compensated for. Radar could not be easily compensated for because it wasn't just a technology. It was the foundation of an entire system of command, control, and information flow that the rest of fighter command's operations depended on. And the proof of that came on August 12, 1940, the day that a single radar station failed and the consequences almost decided the outcome of the entire battle. August 12 was the day Goering chose to open what the Luftwaffe called Adlertag, Eagle Day. This was to be the beginning of the main offensive against Fighter Command, the campaign that would destroy the RAF as a fighting force in approximately 4 days and open the way for Operation Sea Lion, the German invasion of Britain. The actual opening of Adlertag was messy. Signals were confused, the attack was delayed, some formations went ahead without others, and the coordination was poor. But what preceded Adlertag on the afternoon of August 11 and the morning of August 12 was a series of large attacks specifically aimed at destroying the chain home radar stations along the south coast. The attacks on August 12 hit 5 radar stations: Pevensey, Rye, Dunkirk near Canterbury, Dover, and Ventnor on the Isle of Wight. The raids were heavy. Junkers 88's fast twin-engine bombers came in low and fast, trying to hit the radar masts before fighters could intercept. At some stations, bombs fell close to the antenna towers but failed to bring them down, partly because the masts themselves were relatively slender and hard to hit, and partly because the underground equipment rooms and cable runs were fairly resilient. But at Ventnor on the Isle of Wight, the situation was different. Ventnor was the southernmost station in the chain home network, positioned on a cliff above the sea with a clear line of sight south toward France. It was critically important because it covered the western approaches to the Solent and the approaches to Portsmouth and Southampton, 2 major naval bases and industrial centers. The attack on Ventnor was accurate. A formation of Junkers 88s delivered a tight pattern of bombs directly onto the station. The transmitter block was hit, equipment was destroyed, the towers were damaged, and unlike the other stations that had been hit that day and had managed to stay partially operational or recover quickly, Ventnor went off the air. The gap in the radar coverage was immediate and significant. A section of coastline stretching from the Isle of Wight westward into the crucial approaches to Hampshire and Dorset was now blind. Any German formation that approached from the south or southwest in that area would do so without being seen by chain home. The only warning Fighter Command would get would be from the Observer Corps, the network of civilian spotters with binoculars and basic instruments who tracked aircraft visually once they were over land. By the time the Observer Corps spotted incoming raiders, those raiders would already be over Britain. The response to this crisis illuminated just how thoroughly those running British air defense understood what they had built and how dependent they were on it. The people running the filter room at Bentley Priory knew Ventnor was off the air almost immediately. They also knew that if the Luftwaffe realized there was a gap in the coverage, if their intelligence identified the Ventnor hole and directed a major raid through it, the consequences could be catastrophic. So they did something that has been largely forgotten by history, but which stands as one of the most quietly brilliant deceptions of the entire war. They kept transmitting a false signal from the Ventnor frequency. The technical team responsible for the network found a way to continue broadcasting radio transmissions on Ventnor's frequencies, signals that would be detectable by German monitoring equipment, despite the fact that the station itself was wrecked and not actually functioning as a radar system. From the outside, from the perspective of any German electronic intelligence aircraft flying along the coast or any monitoring station in France trying to determine whether the British radar network was still operational, Ventnor appeared to still be on the air. It was a bluff, it was pure theater. There was nothing behind the signal except the hope that the Germans wouldn't probe too hard, wouldn't send a raid through the gap on the assumption that it was actually there. And it worked. The Luftwaffe did not exploit the Ventnor gap. The German formations on August 12 and the days immediately following did not concentrate their attacks through the western approaches where Ventnor had provided coverage. The deception held long enough for the repair teams to reach Ventnor, assess the damage, and begin the work of bringing the station back to operational status. The repair was not instant. Ventnor was significantly damaged and the full restoration of its capabilities took time. For approximately 11 days, the station was either completely off the air or operating at severely reduced capacity. 11 days during which one of the most important sections of Britain's radar coverage was essentially a ghost, maintained by transmissions that gave information to no one. Think about what that means in the context of what was happening during those 11 days. August 13 was the actual opening of Adlertag. August 15 saw the largest single day of Luftwaffe activity in the entire battle, with over 1,800 sorties flown by German aircraft, including a major attack by Luftflotte 5 flying from Norway across the North Sea, an attack that was intercepted and shattered partly because Chain-Home in the north was fully functioning. August 18 became known as the hardest day, with massive raids across multiple sectors and some of the heaviest losses on both sides of the entire battle. All of that happened while Ventnor was down. The gap was there, the vulnerability was real, and the Luftwaffe never used it. The deception, combined with German intelligence's continuing failure to fully understand what the radar network did and how it worked, meant that the most exploitable weakness in Britain's air defense was never exploited. When Ventnor came back to full operation in late August, the relief at Bentley Priory must have been enormous. Because the people running Fighter Command's control system knew, in a way that perhaps no one outside that room fully appreciated, just how close things had come. But the story doesn't end there, because the Ventnor crisis was not the only time during the Battle of Britain that the fragility of the system was exposed. And the way Fighter Command adapted to those moments of vulnerability tells us something important about why the system ultimately held. The issue with Chain-Home's altitude measurement was a constant operational problem. The system could tell you that a formation was bearing 120 degrees, range 80 miles, approximately 50-plus aircraft, but it could not reliably tell you whether those aircraft were at 10,000 feet or 20,000 feet. That distinction mattered enormously. A formation at 10,000 feet was climbing toward the target. A formation at 20,000 feet was already above most of the defending fighters' optimal fighting altitude. Sending a squadron to intercept at 15,000 feet against a raid coming in at 25,000 was a waste of the sortie and potentially suicidal for the pilots. The operators developed techniques to estimate altitude from the way the radar return behaved, from the angle at which the received signal peaked between the receiving aerials. These techniques were genuinely impressive pieces of improvised operational science, developed not in a laboratory but in a concrete bunker while German bombers were on their way. But they were estimates. They could be and frequently were wrong. And wrong altitude information could mean the difference between a successful interception and a useless one. There was also a persistent problem with formations approaching from very low altitude. Chain-Home had a minimum detection height below which aircraft flying low over the sea could simply avoid the radar coverage entirely. The Germans discovered this not because of superior intelligence analysis, but because some of their pilots noticed that at certain altitudes and in certain approach paths, the expected British fighter interception didn't materialize. They flew back and forth until they worked out roughly where the blind spots were. To compensate, a supplementary system called Chain-Home Low was developed and installed during the battle. CHL stations operated on shorter wavelengths and with rotating antennas, giving them better coverage of low-flying targets. But they were installed and commissioned during the battle itself, rushed into operation to plug gaps that were being exploited in real time. The combination of Chain-Home and Chain-Home Low feeding into the filter room at Bentley Priory, and from there to the operations rooms of the groups and sectors, was a system that was simultaneously more capable than the Germans understood and more fragile than the British public knew. There were days when it worked almost perfectly, days when the track of a German formation was picked up over France, plotted continuously all the way across the Channel, and waiting squadrons were positioned so precisely that they were already level at the right altitude, coming out of the right quarter of the sky as the German formation crossed the coast. Those were the days that Fighter Command pilots remembered as textbook interceptions when the whole machine seemed to hum. And there were days when it came apart. Days when the radar operators misread a return or when the filter room was overwhelmed by the volume of plots and gave the operations room a picture that was 15 minutes out of date. or when a sector controller made a judgment call about which of two converging tracks was the real threat and chose wrong. On those days, squadrons were sent to the wrong altitude or the wrong location or scrambled too late, and the German formations reached their targets without effective interception. On those days, bombs fell on airfields, on factories, on cities, and British pilots found themselves bounced from above by escorting German fighters who'd had the altitude advantage all along. The battle was not a smooth triumph of British technology over German numbers. It was a desperate, improvised, continuously evolving contest in which both sides were adapting, making mistakes, suffering losses, and searching for the edge that would tip the balance. And through all of it, through the successes and the failures, the one constant that Dowding and his controllers always returned to was the radar network. Not because it was perfect. It was far from perfect, but because even imperfect radar information was better than no information. Even an approximate picture of where the enemy was, and roughly how many of them there were, allowed Fighter Command to use its limited resources more effectively than it could have done through any alternative means. There's a moment that happened deep in the bunker at 11 Group's operations room at Uxbridge that has become, in retrospect, one of the most quietly dramatic moments of the entire war. On September 15, 1940, the day now commemorated as Battle of Britain Day, Winston Churchill visited the operations room to observe the battle being conducted. He watched as the plotting table filled with tracks. He watched as the controllers ordered squadron after squadron to scramble. He watched as the light boards showing the status of each squadron, in reserve, available, readying, airborne, engaged, filled up from bottom to top until every available squadron in 11 Group was either in the air or preparing to launch. At the moment when every light showed all squadrons engaged, Churchill leaned over to Air Vice Marshal Keith Park, the 11 Group commander, and asked quietly, "What other reserves have we?" Park answered, "There are none." Churchill was shaken. He wrote about it later. There was a moment in which the balance of the battle was so fine, so close to the edge, that there was nothing left in reserve. If the Germans had sent another wave at that moment, if they had had one more substantial formation ready to go, there would have been nothing to stop it. But the Germans didn't know that. They couldn't know it, because the radar picture was a one-way street. Chain home showed the British where the Germans were. It did not show the Germans where the British were or how many of them were left. The Luftwaffe commanders looking at their intelligence on September 15 knew they were taking heavy losses. They knew the RAF was still fighting. They did not know that at that specific moment, Fighter Command had emptied its cupboard completely. That asymmetry of information, Britain seeing Germany, Germany fumbling blind, was Chain Home's greatest strategic gift. It was not just a means of detection. It was a sustained intelligence advantage that, over the 3.5 months of the battle, allowed a smaller force to use itself far more efficiently than a larger force that was flying into the unknown. The German pilots were brave, experienced, and flying excellent aircraft. Their bombers were well built. Their tactics were professionally developed. But they were fighting in the dark, making decisions based on incomplete and frequently wrong information about what was waiting for them on the other side of the channel. And the British pilots, guided by controllers who were reading a radar picture, were fighting with their eyes open. The disparity in performance per aircraft sortie was striking. British fighters, guided to their targets by the radar system, typically made contact with German formations far more consistently than the German records would suggest should have been possible given the size of the defending force. Fighter Command was not larger than its records showed. It was just used better. The efficiency of Dowding's system extracted more defensive effectiveness from each available aircraft than a pure numbers comparison would ever predict. Now here is the part of the story that rarely gets the attention it deserves. Because it's one thing to describe how Chain Home worked in principle. It's another thing entirely to understand who actually made it work. Who was sitting at those cathode ray tubes, watching those blips hour after hour, making the split-second decisions about what was real and what was ghost return, what was a raid of 50 and what was a raid of 500. In large part, the answer is women. Young women, many of them in their late teens and early 20s, many of them with no technical background at all before the war, who were trained to operate the equipment and then assigned to do it for 8-hour shifts, rotating around the clock, 7 days a week, in concrete bunkers that were themselves potential bombing targets. The Women's Auxiliary Air Force, the WAAF, provided the majority of the radar operators, the filter room plotters, and the operations room controllers who made Dowding's system function. These women were not in auxiliary or supporting roles in the conventional wartime sense of that phrase. They were at the operational heart of the air defense system. Their work was not the same kind of work the pilots did, it was not physical in the same way, and the consequences of failure were different, but it was just as important and in some respects more technically demanding. A radar operator watching a cathode ray tube in 1940 was doing something genuinely difficult. The returns were noisy. The screen showed not just the real echoes from aircraft but reflections from the sea surface, from hills and cliffs, from weather systems, from other radar stations interfering with each other. Distinguishing the real signal from the clutter required both training and experience. It required the kind of pattern recognition that becomes intuitive only after hundreds of hours looking at the same equipment in the same location. The filter room operators were doing something even more cognitively demanding. They were receiving voice reports from multiple radar stations simultaneously, each giving slightly different data about what appeared to be the same formation and reconciling those reports into a single coherent picture in real time. A filter room on a busy day during the Battle of Britain was a place of controlled chaos. Voices coming from every direction, plots being called out and checked, positions being calculated mentally under time pressure. With the knowledge that every extra second of delay between a radar return and a plotted track on the operations room table was a second subtracted from the warning time available to the controllers and ultimately to the pilots. These operators rarely got the recognition they deserved, either during the war or afterward. The story of the Battle of Britain was told for decades primarily as the story of the pilots, which is understandable and not entirely wrong. The pilots were the most visible participants and the most immediately at risk. But the story is incomplete without the women in the bunkers and the filter rooms, and it is most incomplete of all when it forgets what they were working with and what the system they sustained actually meant for the outcome. There is another dimension to the Chain Home story that connects it to a much larger question about how Britain won the Battle of Britain, which is the question of industrial capacity and repair speed. The Luftwaffe's strategy evolved during the battle. In the early phase from mid-July through to mid-August, the attacks focused on shipping in the Channel and on the radar stations and forward airfields. Then, in the period roughly from August 13 to early September, the focus shifted to destroying Fighter Command's infrastructure, the sector airfields where the squadrons were based, the operations rooms, the fuel and ammunition stores, the communications networks that connected the radar stations to the filter rooms and the operations rooms to the squadrons. This was actually the most dangerous phase of the battle for Fighter Command. The attacks on the sector airfields at Biggin Hill, Kenley, Hornchurch, Debden, North Weald, and others were damaging in a way that the attacks on radar stations despite the Ventnor crisis ultimately were not. The airfields were hit hard, operations rooms were destroyed, runway craters appeared, fuel lines were cut, ground crews were killed. And here is where British industrial and organizational capacity showed its quality. The repair speed was extraordinary. A runway cratered by a 250-kilogram bomb could be filled and made operational again within hours. A damaged operations room could be relocated to a nearby building, a pub, a requisitioned cottage, a converted garage, and have its plotting tables, telephones, and communications restored faster than the attacking formation was back in France. This resilience was not accidental. It reflected both organizational preparation, the pre-war planning that had established repair teams and logistics chains, and human ingenuity, the ability of the people on the ground to improvise solutions to problems that no training exercise had ever specifically anticipated. But the Chain Home network was different in one important respect from the airfields. Airfields could function at degraded capacity. Bombed runways could be operated around the craters if absolutely necessary. Operations rooms could be moved, but the radar masts were fixed. They could not be relocated. And while the equipment rooms could be repaired and the electronics replaced, the towers themselves required significant structural work to restore after serious damage. This is what makes the Ventnor deception so significant. The alternatives to that deception were all worse. You could not move the Ventnor station. You could not quickly rebuild it. You could not replace its coverage from any other existing installation. If the Luftwaffe had understood that the coverage was gone and had exploited it aggressively, the options available to Fighter Command in the southern sector would have been severely constrained for nearly 2 weeks at the most critical period of the battle. What the deception bought was time. And in the summer of 1940, time was the one resource that mattered above all others. Time for the repair crews to work, time for Ventnor to come back online, time for the battle to continue without the catastrophic exploitation of a gap that the enemy didn't know existed. It is worth pausing here to consider the counterfactual. Not because counterfactual history is a precise science, it isn't, but because thinking through what might have happened is often the clearest way to understand why what actually happened mattered. Suppose the Luftwaffe, after the attacks on August 12, had sent their electronic intelligence aircraft to verify that Ventnor was down. Suppose they had confirmed it and passed that information to their operational commanders. Suppose that Goering had immediately organized major raids through the Ventnor Gap, coming in from the southwest at low altitude and at maximum speed, aiming to hit Portsmouth, Southampton, and the naval facilities along the south coast. Without Ventnor's coverage, those raids would have crossed the coast before Observer Corps could give meaningful warning. The controllers at 11 Group would have had partial information at best. The sector controllers responsible for that area, Tangmere primarily, would have been scrambling squadrons based on fragmentary reports without the altitude information and track data that made interceptions reliable. Some squadrons would have made contact, others would have missed entirely. The bombers would have had more time over their targets. Now suppose this had continued for 11 days with major attacks through the gap every day. The damage to Portsmouth and Southampton, both of which contained critical naval repair facilities and supply lines for the Royal Navy, could have been substantial. The morale impact of seemingly unopposed German raids appearing over southern England without warning could have been severe. And the operational wear on 11 Group squadrons scrambling into confused interceptions, taking losses in unfavorable circumstances, could have accelerated the attrition of pilots and aircraft at exactly the moment when replacement rates were already dangerously low. Would this have lost the Battle of Britain? That is genuinely impossible to say. The battle had many interdependent variables, but it would have made it significantly harder for a significant amount of time, and in the conditions of August 1940 when every day counted and every squadron mattered, harder and longer might have been the difference between survival and collapse. The deception held, Ventnor was repaired, and the battle continued. There is one more element of the Chain Home story that deserves careful attention, and that is what the system represents in terms of how a nation prepares for war it doesn't yet know is coming. Watt's first successful radar demonstration was in February 1935. The first operational Chain Home stations were installed by the summer of 1937. By September 1939, 19 stations covered the critical coastline. By the summer of 1940, when the battle began, the network was complete enough, staffed enough, and integrated deeply enough into Fighter Command's operations that it was genuinely ready to do the thing it had been built for. That is a development timeline of approximately 5 years from laboratory demonstration to operational deployment of a national defense network, running alongside the design and procurement of the aircraft the network would guide, the construction of the operations rooms and filter rooms the network would feed, and the training of the thousands of personnel who would make the whole system work. 5 years in peacetime, partly in secret, with a government that was simultaneously trying to avoid war, appease Germany, and balance a defense budget against competing national priorities. The fact that it happened at all is extraordinary. The fact that it happened in time is almost miraculous. There were moments when the program nearly died. There were budget arguments, technical setbacks, priority disputes, skeptical officials who thought the money would be better spent on more aircraft or more guns. Watt and Tizard spent a significant portion of those 5 years fighting bureaucratic battles as well as technical ones. The key figure in keeping the program alive, less celebrated than Watt but in some ways equally important, was Frederick Lindemann, Churchill's personal scientific advisor, a man of strong opinions and considerable intellectual arrogance who nevertheless understood the military implications of radar and championed its development at a time when champions were needed. There was also Air Marshal Hugh Dowding himself, who understood radar's potential implications for air defense doctrine before most of his colleagues, and built the entire command and control architecture around the assumption that radar would work. If Dowding had been a conventional air commander, if he had built his defensive strategy around standing patrols and visual detection, the infrastructure to exploit radar effectively would not have existed when the battle came. This is the often missed lesson of Chain Home. The technology alone was not sufficient. You could have had every mast built and every cathode ray tube installed and every operator trained and still lost the battle if the operational and